Good morning, ladies and gentlemen. And first of all, I want to thank the organizer for inviting me here today to give you the latest insights into the occupant in vehicle safety, the research results, and also, of course, revisit beautiful Korea. It's fantastic to be here. So a bit about myself, so you know where I'm coming from. I'm an engineer. I have a Master of Science in Engineering Physics and a PhD in Mechanical Engineering. And I'm related to as Associate Professor at Chalmers University in Sweden. This talk will be on a specific topic. It will be crash safety. It's about protection of the occupant in the case of a crash. And it's one particular injury that is in focus, and it's the whiplash injury. So starting with, see here. This is the situation in the crash lab. We have a norm. We call it the model of the human, and it's a man. Here you see the crash test dummy Hybrid 3 lined up to be used in crash tests, where we assess the protection performances in the event of a crash. We have for certain crash configurations something called fifth percentile female, which is actually a scaled down male in terms of height and weight to that of a small occupant. And then we have a large occupant, which is called the 95th male, to make the have models that represents the outliers in terms of model of human. So this is the situation in the crash lab, and I will show to you why this is a limitation. First, about whiplash injury. They account for approximately 70% of the cost for all injuries leading to permanent medical impairment for the insurance companies. If you look at different injuries to different parts of the body, neck injuries, whiplash injuries is over 70%. And then you have all the other injuries as small bars. In Europe, we have around 800,000 injuries annually, and around 40,000 of these resulting in long-term suffering to the cost of over 10 billion euros in Europe. And you have a similar situation reported from all over the world. These injuries, they can occur in all impact direction. However, since they are found in low severity impacts, which is around between 15 to 25 kilometers per hour in change of velocity, they are most common in rear impacts, even though the risk of such an impact is actually higher in frontal, but the low severity frontal impacts are very rare. What we see in the injury statistics is that we have very different levels of protection in different car models, and also in same car models, but with different seats. So the seat and the design of the seat is crucial here. I will spend some time on the hypotheses about the injury mechanisms, because this is important in terms of the models of the human that we use. The hypotheses about the injury mechanisms are very early in the event. It's in the so-called retraction motion, when the head is moved forward relative to the torso. It looks like this. It causes, excuse me, it causes an S shape of the neck, and in that S shape you have loadings on the structures of the neck that can cause these long-term symptoms. As a PhD student at Chalmers University back in the 1990s, I did a literature review on the whiplash injuries because I was in a project where we developed the world's first physical model for rear impacts. That model was based on the norm, the average male, and the dummy that we have available. When I did the literature review, this was what I found. You can see here the risk of injury for males is normalized to 1, and then you see the risk for females in compared to the males. You see here that since the end of the 1960s onwards, we have the same situation. Females has shown to have a larger risk of injury than males. This is very, or rather uncommon in a scientific area, that you have consistent data showing only one trend in one direction. But here it's from all over the world. Some are specific car models, some are bigger ranges of models, and all data the same. So as I said, I was in the project where we developed this dummy. This is from the then late 1990s, and it was a collaboration between vehicle industry and Chalmers, and this was then the first step to have a model at all, a physical model in the crash lab. At that stage, we hoped that this new model would make it, would change the situation so that we would protect actually both males and females better in the future than we had been able to do, and that this model would make that happen. However, when we, 10 years down the track, looked at the whiplash protection systems that had been developed, this is data from 2010, we saw that the systems with whiplash protection, the seats with whiplash protection system protected the males better than the females. And then you should remember that the females were worse off from the start. So we were not enough in the right direction. We know how to do things even better, but we weren't able to do it for the whole population. So EU funded project was established. I coordinated this project, and we did run from 2009 to 2013, where we aimed at developing the first model of an average female at all. We did it as a starting point with developing a virtual model. So using computer simulations to compare the response of the male and the female. Still with the aim or hope that we could maybe scale the injury thresholds for the male or something like that and therefore improve the situation. This is the model that we developed, and it's based on data that we then found in the literature. It's the same set of data that was used for developing the average male. In those background studies, which is published, the data for the average female also exists, but it has never been used. Nobody has used it. So we used it to develop this model, and yeah, you see the different parts of the project where we of course also looked at criteria, injury criteria, and here comes the important part of this neck, because differences between males and females that are of high importance here when it comes to the interaction with the seat and the dynamic response is, for example, among others, the stiffnesses of the joint in the neck. And that differs between females and males because of differences in dimensions of the vertebra. That's one part, but also the strength of the muscles. So that in combination with different geometry, different center of gravity, and different dimension of the various part of the torso makes the interaction with the seat in the event of a crash quite different. It can be, depending on the design of the seat. Here you see the average male and the average female side by side. You can see some of the geometrical differences and also the differences in height, total height and weight. To give you some example of how this can influence in a crash is, for example, one seat that you can see here that we used with the two dummies with. And it turned out that in the head restraint, in the seat, there was a bar. And this bar, in the standard test setup, the male dummy would interact with that part of the head restraint and therefore have a nicely controlled dynamic event during the crash. However, when we had an occupant that were about 10 centimeters shorter, the average female, she would miss that bar and have a totally different dynamic interaction with the seat. And this, of course, you can only see if you have various models. I said that we don't have a physical model yet, and that's the case of an average female, but what we did was that we scaled down to make some physical tests to see, does this really work also when we have different seats? So we scaled down average male model, and here you can see the Biorid 50F as the scaled down model is called, and the 50F and the Biorid 2 is positioned in the same seat. And for me as an engineer, it was really interesting in the crash lab because I had the expectation of where the dummy would be and how big it was, and all by sudden you have an occupant model that has different proportions. And of course, we tested 4 seats, and they showed that for some seat designs, we did have a very different type of response. Finally, I want to share with you this recent data. This is, I go through this slide, I know there's a lot of information in it, but it is important. This is about the whiplash protection systems. It's risk of permanent medical impairment. This is insurance data. It's standard seats, it's seats with an active head restraint of some kind, RHR. And then there's a group of seats called Will and Whips. That's the Volvo seat and the Toyota seat. This is an example of how important it is to have data divided into males and females in this case, but also how tricked you can be by just looking at the overall picture. The green bars shows you the standard seat, the seat with the active head restraint, and the Will and the Whips. So looking at the green bars, you would say that, oh yes, we have improved the system. Some would do even better than others, but we are on the right track. When you divide the data into males and females, you can see that, and that is the blue bars males, the red ones females. You can see for the protection systems with an active head restraint, the male benefit get the whole benefit, and if any effect for the females is actually worse than to be in a standard seat. The Volvo and the Whips, the Volvo and the Toyota systems works well for both occupants, but also here you have a little bit higher benefit for the males than the females. So this is the situation today, and so for my final slides, we have talked during this summit, and we'll continue to talk about improvement in terms of opportunities, business opportunities, and making products and being in the front as an industry. Here, I think that if the companies that embraces that this is of importance will have a fantastic front position, and we do still lack to improve evaluate the safety performances in terms of how it protects the whole population, in order to promote for the consumers the products that actually are the very best ones in terms of safety. And I think that I hope that before I retire, I see this happen. Thank you for your attention.